Okay, so now we'll ask the question, will a melting Arctic ice cover cause sea level rise? And there are two options. Yes or no. Now I want to clarify that by Arctic ice cover I mean the sea ice cover, which is just frozen ocean water. And that is important because in the Arctic you also have the Greenland ice sheet, and that's not what I'm talking about right now. Not the Greenland ice sheet, which is ice that sits on land. And I have chosen this question because it is a nice illustration of Archimedes' principle. Which brings us to our sketch of Archimedes. Big head, strong eyebrows, and great beard. So let's consider a block of ice sitting in water. And we're considering a cuboid of dimensions h, height, length L, and width W. And so the area is L times W. Now the part of the cuboid that is submerged has a draft d, that is the distance from sea level to the bottom of the ice, and then the part above the sea level is called the freeboard. Now the question is, when this block melts, will the meltwater take up more space than the water displaced by the floating ice? And we'll use two principles of physics to answer this question. The first one being force balance, or more particularly hydrostatic equilibrium. And the second one is conservation of mass. The force balance tells us that the buoyant force acting on the ice block upward from the displaced water has to be balanced by the gravity acting on the ice. So Fg plus Fb has to be equal to 0. Now Fg is just minus m, the mass of ice, times g, plus Fb, and Fb is the mass of the displaced water times g. We can see that we immediately can cancel the g, and so the mass of the ice has to be the same as the mass of the displaced water. Now, mass of ice is the density of ice, rho I. Should add this here, rho I, and rho W is the density of water. Rho I times the volume of the ice has to be the same as rho water times the volume of the water. But the volume of the ice is just H times L times W, and that has to be the same as rho W times the volume of the water, which is D times L times W. So we can cancel LW, and you're left with draft D is H times rho I over rho W. Now the conservation of mass tells us that the mass of ice has to be the same as the mass of the melted water. I'm using the liquefied here, and so if we have rho I times Vi as before, that would be rho L times VL. And now we're just considering that we're distributing the meltwater over the same area A, so we still have rho I H times L W is rho L. And let's call this depth X, and the area LW. Yeah, so we're filling the same area as the displaced water, and we're wondering how large is this height x. And so again, you can cancel LW on both sides, and you're left with x equals rho I over rho L times h. And so let's assume, for the purpose of this example, that rho L, the density of the liquefied ice block, is the same as the density of the water surrounding it. And that is typically approximately true. And so in this case, x is rho I divided by rho W times h. And we have just shown that that number is d. So the depth of this area of water that is filled with the liquefied ice, with the meltwater, is the same as the depth of the displaced water. And so that means if you melt a block of ice, the volume of water that is filled with the meltwater is exactly the same as the volume of water that was displaced by the floating ice block. And as a result, a melting Arctic sea ice cover will not cause global sea level rise.